We continue with black holes and horizons, and we're going to discuss surface gravity and its relation to temperature and the laws of black hole mechanics. And so I think that as estimate, I should do a reassuring estimate that is, are black holes forever? How long do they last? If they emit radiation, they're going to shrink. But these are laws for equilibrium black holes, the classical ones and the quantum ones. And so how is that compatible with the fact that they evaporate and they run away and they explode? Is it equilibrium or not equilibrium? And the way to settle it is you estimate how long it takes, and you know what time scale you have to trust the estimate. Okay? So the objective is considering Hawking radiation, what's the lifetime of a black hole? And let's try. I haven't time it. Let's see if I can do it in 3 minutes. So I want the lifetime. So what do I gonna need? I need the temperature. And we discussed this already. It's a quantum effect with h bar over m. And I need the power radiated. Power just means how it changes in energy per unit time. And yeah, I can use Stefan Boltzmann law. Stefan Boltzmann law is area temperature to the 4, because I know that this is black body radiation. And area, we know area is m squared, radius squared. So from here I get h bar over m squared. And then what's the mass loss formula? Mass loss m dot, this is E dot, equal minus energy radiated, minus P, which is minus h bar over m squared, which I can write as E m cubed h bar, which gives me, or I don't need the law, I don't need to solve this equation, I just need the time scale. Time m cubed. So this is the theory part. Time scale is going to go this way. Now I want the estimates. Making it into an estimate, I need numbers. Let's see if I can put in numbers. So first I write it in a way that makes sense as units. So it's going to be m, initial mass of the black hole, over mass Planck, Q. I pay this one. And then yeah, there's the Planck. And I promise I will keep the h bar. There's an h bar here. If h bar goes to 0, lifetime goes to infinity. So let's see. Mass Planck is 10 to minus 8 kilograms. T Planck is 10 to the minus 44 seconds. Let's see what happens for Sun. Mass Sun is 10 to the 30 kilograms. So I need tau that is 10 to the 30, 10 to the 38, 38 cubed, 10 to the minus 44 seconds. No, so to do this, this is 120 minus 6, 114, 114, 4, 10 to the 70. And 1 year is 10 to the 7 seconds. So this is 10 to the 63 years. It's infinite. These things lives forever. Real timing. 3 minutes is what it takes. It lives forever. No, like lifetime of the universe from hot Big Bang till today, 10 billion years. So 10 to the 10. This is 10 to the 63. Should I even believe the number? No, that really requires that you believe physics over a time scales that is many ages of the universe. And you could argue that, well, can we trust the laws that we have? If it's a positive cosmological constant, things are going to keep them. If what we see as acceleration today is really due to positive cosmological constant, then everything is going to dilute. There is no new physics to discover at late times. It's a boring scenario. And so maybe we should trust this if you are patient and wait 10 to the 63 years. But this is assuming that nothing falls in the black hole. If something falls in the black hole, then it lasts longer. Okay? So maybe you should take it as, if you're working in solar mass black holes, this phenomenon is completely negligible. Don't even take it into account. There are many other things that are way more important, like CMB is going to accrete into the black hole faster than this. However, you see how it goes. If I have a 1 kilogram black hole, that I'm holding here, 1 kilogram black hole, you have 1 kilogram, 10 to the minus 8, 10 to the minus 24. There's a 44 in 10 to the minus 20 seconds. Poof. And poof is not the right sound, it's an explosion. You have 1 kilogram, 13 Hawking radiation within it's 10 to the minus 20 seconds. You didn't react to me saying I'm gonna hold 1 kilogram black hole. How do I hold that 1 kilogram black hole? Like, it's not that heavy. If there was a handle, I could hold it. But is there a handle that I can attach the black hole to hold it here? Suppose that I have it. Before we discuss all this, I think I should have the rest of 1 kilogram. How do I hold a 1 kilogram black hole here? I cannot put it on a table. The answer is going to be relevant for things that we're going to discuss. So let's think about it. It has nothing to do with quantum. It has to do with solar mass black holes, classical. So 1 kilogram black holes, well, they disappear quickly, but could you even keep it here? How do you hold it?
What if it is charged?
Good. That's a way to put something you can attach to. No, if it's charged, then I would say I put an electric field, so it would fall. I put an electric field this way, if it's positively charged, so it'll be pushed up. How big should the electric field be? I have to hold 1 kilogram. How much? Suppose that I put, like, I cannot make here in this room an electric field bigger than 10 to the 6 voltmeters. So otherwise I get a spark, right? And it discharges my capacity. So how much charge should I put so that I can do it with an electric field that I can make in a lab without making a vacuum? The thing that I want you to see is that the charge would have to be so big that you cannot put that charge in this black hole. It's larger than the maximum charge that you can put in a black hole of this mass. Okay? Then you would say, well, but then it's because you put the electric field too small. Do a vacuum, do stronger electric field, and see if there's enough charge. You can play with it. No, say, try and check. And you're going to see that, well, if I make an electric field, I certainly cannot make an electric field bigger than as energy in the electric field larger than MeV. It's going to start producing electrons and positrons and discharge not with a spark that is in air, but is this Schwinger effect. It's going to polarize the vacuum and get a spark of electrons and positrons and discharge my capacitor. So I believe say you are not going to be able to hold this. You can try also for 1 gram. You're not going to be able to. So what happens to this black hole? Falls. What happens after it falls? A 1 kilogram black hole, I let it go, but I couldn't hold it, but I can make it maybe. What happens to it? It goes and then 1, 2. Elliot.
Oh.
Okay, and then
Depends how much mass is accreting. If it's doing that at a good rate, then it grows. Otherwise, it perishes.
I see you are looking at accretion, but what's the cross section of 1 kilogram? Is it this big? So is it gonna accrete? We need to do these things. You have to have a clear sense of what it is. You have a 1 kilogram black hole. It's 1 kilogram. But what's the cross section? What's the area? If it was 10 micrograms, it would be 1 Planck length. It's 10 to the 8 of this, it's 10 to the 8 Planck length. It's not going to see any atom. It's going to go through the Earth without touching anything. Like people say neutrinos pass through. The Earth is opaque to neutrinos compared to 1 kilogram per course. The Earth is completely transparent to 1 kilogram. Okay, so you can forget. That's why I want the estimate. You can forget completely accretion. You can forget completely friction because it doesn't touch anything. And so I let it go here. What happens? Huh? Yeah.
There's a geodesic.
Yes.
But I'm letting it go radially. Just force. What happens? It arrives at the center and then keeps going.
Oscillates.
Oscillates. Okay, so you're probably seen this weird exercise in mechanics. You draw a tunnel that doesn't make sense. How do you make the tunnel? Okay, this one you don't have to make the tunnel. It goes through, no problem. How long before it comes back? You let it go, arrives on the other side, then comes back, and we see it again, and we can detect it. Put a small charge and check when it comes back. How long? Millisecond, second, year, million years. How long?
Related to the time scale of the Keplerian, but there's the same quantities and
Millisecond, second, hour, days. What the number? Argument? Hours is good. Hour, argument?
I just remember that the period of throwing that person in the tunnel is hours.
So you did the calculation. Good. That's a point. No, you see, I did the calculation, so I know the answer. And you should have got 83 minutes. Okay. Or 90 minutes. ISS goes around, takes 90 minutes. That number you have to know. ISS goes around in 90 minutes. You see it in the sky if you check quite a few times per day. You go around, you go through. This is just the same orbit. It's just that one is elliptic this way, and the other is elliptic very narrow. Same imaginary axis is the same period. Okay? And if this was on another rocky planet, that's another calculation to do. Is 83 minutes is from the surface of any rocky planet. Because it just depends on the density of rock and nothing else. Okay. One more estimate. No, you didn't give you a chance to ask about this estimate. We went into something else. Questions about this estimate of the lifetime? Yes.
So when we're integrating the dm cube over dt, there should be a constant, and why are we sure that the constant isn't huge or like negatively huge as well?
Yeah, so let's do it more slowly. So first here there's some minus, the mass goes down. Then you say I have to integrate this differential equation. There needs to be an initial condition. That's the mass of the initial black hole. So you should put a knot. It's the time of disappearing starting from an initial mass. Can be more precise. If you solve this differential equation, you find m of t. I can solve it, but no, it's gonna be initial mass minus mass cubed minus t cubed, t over tau and better 1 minus t over tau cubed over 1/3 initial mass. So you see there's here the initial condition, and here this tau that is the typical time development. And so when this t equals tau, the mass is 0. And this is just like solving this differential equation. It's linear, so there's only one initial. Okay?
When t is infinity,
When t is 0, it's the initial mass.
Yeah.
When t equals tau, the mass goes to 0. So the mass does something like this. It's m of t. But if you send t to infinity, you pass this point, the mass will.
okay,
You cannot trust this solution anymore. In fact, here at the end point, this thing is going to become Planckian. So there you need neophysics. Or maybe even more, because there could be cumulative effects that we are neglecting. Because this calculation is that every single time there's a small effect, and we just integrate that. We didn't take into account there could be cumulative effects that are over a long time, like for Fermi-Golden's rule. Probability goes down exponentially, but it cannot be exponential forever. No, there are cumulative effects, even for decay of atoms. Okay. So these 90 minutes, 1 hour and a half, have it always quick. If I ask what's the curvature here, we have learned curvature is 1 over length squared. That length, do you remember the number? Like, if one says it's 10 astronomical units, how do you fit 10 astronomical units here? You cannot. We are speaking about curvature here measured by a spring here. If you think of it not as a length, but as a time, that time is 90 minutes. That means that if I put like some rigid pendulum and I look at curvature effects, the pendulum is going to oscillate with a period of 90 minutes. That's the effect of curvature. Okay? Okay. So we are ready for going back to horizons. The notion, the technical notion is this one, killing horizons. The physical meaning is surface gravity. I tell you first about the mathematics, then why people call it surface gravity. Not as an analogy, but as something that you can measure. Okay? The best place where to read this is these notes of 1000. They are all online. I should probably put on the Canvas page a list so that it be easier to find. So let me start with the mathematics. It's going to be a bit obscure, but so that we have the names of everything. So what are the ingredients? Space-time is given. It's a space-time that is asymptotically flat, is an isolated gravitating system. I'm also going to assume it's stationary. Nothing changes in time. And to be precise, when I say stationary, I have to say it like in non-relativistic mechanics, stationary means things don't change in time. But in general relativity, you have to say time measured by what clock. It's not, it's going to be stationary for every clock. So for which clocks? And so Killing vector is a way of saying there is a specific time translation symmetry along word lines that have this as a tangent vector, and stationary means that this Killing vector is time-like. I'm using the word Killing vector freely. I should check, is this a notion that you're all familiar with or not? Should we go back and say what are Killing vectors? Anybody wants to tell me what's a Killing vector?
The Killing vector, vector along which the metric doesn't change.
Good, exactly. So you take, for instance, a sphere, you rotate it this way, and it doesn't change. And so you say that this direction as a tangent vector, it's a vector, and that vector is a vector that, so more mathematically, you can say you take the Lie derivative with respect to a vector of the metric. If this one is 0, then psi is a Killing vector. Should probably say it at least once, not because it kills anything. Killing is the name of the person who came up with the idea. It's actually pronounced killing. And if you work it out, this is this equation. So once you find a vector satisfies this condition, then you know that the metric has a symmetry. And so instead of saying symmetry, we say Killing vectors. And so when you say stationarity, it means that this thing is time-like. Note, I'm not going to assume it's time-like everywhere. It's enough that it's time-like far away. Okay? And now I'm ready to introduce this definition of horizon. It's different from any of the ones that we discussed before. The ones that we discussed before didn't require any symmetry. This one requires a symmetry. It's called a Killing horizon. It's a null surface by definition, and it's a null surface where this time-like Killing vector that is time-like far away is the place where it becomes null. Time-like, it could be an asymptote where it becomes null. That asymptote, you call it Killing horizon. Yes.
So if there are multiple time-like killing vectors, does that lead to a contradiction?
No. Minkowski space has Poincare symmetry, has 10 generators, so there are 10 Killing vectors.
Right. Yeah.
Okay. Rotations are space-like, spatial translations are space-like, but time translation is time-like.
Yes.
And boost is also time-like.
Oh, yes.
So you have two that are time-like. They are both Killing vectors. So let's go check. Let's do exactly what you said, Minkowski. So first in Cartesian coordinates, inertial time translation, so the Killing vector dt, these translations. There's another Killing vector that is the one of boost. You take something, you boost it, it follows this hyperbola. These are, if you want, curves that one would follow if one has constant acceleration. I'm on this one with acceleration 9.8 meters per second square, and you are too. You're not following this one. Just don't forget. You're doing Minkowski. Don't think that you are on a geodesic. You're not on a geodesic because the Earth is pushing you. Okay? So you're following this time-like Killing vector. Now, this is time-like, but then there's a place where it becomes null, and then it becomes space-like. And so if you follow the logic that I was describing, this Killing vector defines a Killing horizon for Minkowski. That's what people call the Rindler horizon. Yes.
So the red lines are, they're not the DT. Those are not DT, right?
No, these are the, let's say, if you use coordinates eta rho, it's d in the eta. Yes, the hypercoordinates, exactly. And so if you draw the Penrose diagram, you see that the time-like Killing vector for Minkowski that are the inertial ones are these ones. And these ones that have constant acceleration are these ones. And so they become null here. So it defines a Killing horizon. However, they don't satisfy the condition that I was saying before, that they go time-like far away, because here they go null also. So sometimes people call them a Killing horizon, sometimes not. Depends on how seriously you take the list of requirements for calling it a Killing horizon. Okay? Yes.
What's the Killing vector that corresponds to the time translation crosses the null surface?
Yes. So yeah, you mean yeah. So it crosses this null surface. That's what you mean?
Yeah.
Yeah.
Yeah, because we were saying that null surface is the boundary between the timeline and the space-like Killing vector, but also there's a Killing vector that crosses that surface.
Yeah. And this is in the same sense as there's the outside of a black hole and there's the inside of a black hole, but you can still cross the horizon. You can fall into the black hole.
Right, so the surface is like the surface between two particular Killing vectors. Like it has to be the red
Ah,
and the green.
I see what you're saying. So the standard way people name these things is it's a field, it's a killing vector field. In this killing vector field, this green part and this red part, they are parts of the same field. The field is defined everywhere. And then on this portion, that field is as time-like killing vector. Nothing. It's a vector field. So the vector field is defined everywhere. And it's time-like here and space-like here. And null here. And in this point, it's not really well defined. No, they call it a bifurcation space.
So the time translation killing vector that is not, it's not existing this vector field, or it's a different vector field?
It's a different vector field. No, you have this D in dt that is a time-like killing vector, and this D in d eta that is also a time-like killing vector.
So both the green and the red are derived from actually.
Yes, yes. They are both boost killing vectors. Or like they are the boost killing. Okay, let's do Schwarzschild now. Let's do Schwarzschild. I'm gonna first do Schwarzschild coordinates r areal radius and t the t of tangent vectors of stationary observers outside. If you are on the surface of a star, you are a constant radius, you are time-like, you have an acceleration, nothing is going to change around you, you're the surface of a stationary star. So this is a killing vector. It's d in dt. We can check quickly. You look at the metric, there's no time in the metric. This is clearly clear. Note, however, that inside a black hole, this same dt is space-like. You're calling it dt, but the name doesn't mean that that's the property. The name is just a bad name. T. It's space-like inside, it's time-like outside. Somewhere in between changes sign. It's null. This is what is called the killing horizon. Killing horizon is find a time-like killing vector, find that killing vector that's far away is time-like, and find where it changes properties. Where it changes properties, that defines the killing horizon. If I go back to this one, the killing vector is this one that we are speaking about. And there's a place where it becomes null. Then if you go inside, it becomes space-like. There's also this other unphysical part. If you keep extending, you find that here it goes backwards. So when they say that here there's a universe, here there's another universe, you should also remember that it's upside down, the other one. No, the killing vector goes down if you want to really to make sense of it. Okay? There's a theorem, a rigidity theorem, that tells you that if you have a black hole that is stationary, and you look at the event horizon of that black hole, and the event horizon defined as the boundary of what can affect the future, then it is a killing horizon. Okay? It doesn't go the other way around. Yes?
It seems like every killing vector field can potentially have a killing horizon.
Yes.
So does that mean you can have different killing horizon for the same one?
I see the question. It's a good question. Can you find a space-time that has two time-like killing vectors? I don't know one example. Like if you go in Minkowski, you have two time-like killing vectors. One has the property that it's time-like far away, which is this one, and it remains time-like everywhere, and so there is no horizon. And the other, the boost one, changes sign, so it looks like it will give you an horizon, but far away is not time-like. And so I'm just saying, in this example, nothing goes wrong. In this example, there is only one that is time-like, and so also nothing goes wrong. There's probably another thing that I should add that is, we're speaking about symmetries. And so I see the concern. You could have like two notions that don't match, but in 4 dimensions, you can list at most how many symmetries you have. It's at most 10 Killing vectors, like Minkowski and de Sitter. And so you can go through a list and check what can go wrong and go by elimination. So my answer is, by elimination, I know that that concern never arises. But I don't have a theorem to say that they cannot. Okay, it's really, I'm going through the list in 4 dimensions, and I know that it doesn't happen. Yeah, at least for general relativity. Yes.
So why is the boost Killing vector not time-like? Why?
You see it here. So if you go this way, it becomes null. But also if you go this way, it becomes null. No?
How do I see that on the other?
Yeah. Take the word line of a particle with finite acceleration. And then you ask what happens if so this one is if you send the acceleration to infinity. And this one appears as if you're sending the acceleration to 0. That is true. And so one would say this becomes time-like. But you're doing it in such a way that you're not just sending the acceleration to 0, but you're also sending the particle farther and farther away and time-like. And so it's the limit of it's going to become this one. That's the calculation to do. And if I turn it into a formula, it should be clear. You just take this same mu and you look at the normalization. And it's not. Yes.
We could diamond with the light constant. This one will be the other one, right?
Yeah. And then let me be more clear. The point is this endpoint here. Let me try to address more precisely this question because you have a point like how about these lines? These ones far away, they also do what I was saying, that is they go closer and closer. So I haven't addressed your question yet. To address the question completely, I have to answer the endpoints. So this one goes from here to here. These ones, I'm saying go from this point to this point. So how do I explain that? It's a matter of orders of limits. You can say, fix the acceleration small and go far away. If you wait long enough, even if you have a small acceleration, you have this acceleration forever, and you're going to reach the speed of light. On the other hand, if you do the ordering and the limit in the other order, you say, fix first the time interval, and then you send the acceleration to 0, and then you send the time interval to infinity, then you go from here to here. And so it's one of those standard things where there are 2 limits, and it's important the order of limits. Okay?
So far away means far, like large X?
Yes.
And the Schwarzschild case large R.
Yeah. Good. Let's put some physics into this, because at this point, this is just symmetries and places where symmetries behave in an expected way. Okay? I want to connect it to the notion of surface gravity. Surface gravity is the thing that people in Newtonian mechanics call it. Here, surface gravity is 9.8 meters per second square. Just means acceleration. Why don't people call it acceleration? Because in Newtonian mechanics, people got confused and they started calling acceleration the wrong thing. You know what I'm speaking about. No. This thing that forces 0 acceleration is the one that stays here that is accelerated. No, gravity is, it's not a force that pulls, it's the table that pushes things. Newton got it right for centrifugal things, but he missed it for gravity. No? you don't speak, you don't say the centrifugal force, even though sometimes you use the word. You know that that's just acceleration. I'm referring to that. And so this name surface gravity is, again, you could just say acceleration, but everybody says surface gravity. Okay, so let's do that. We said we have an asymptotically flat space-time. We have a Killing vector. Killing vector means it solves this equation. And we also have that far away, it's time-like, so I can normalize it, -1. This is important, this normalization, because to give it an interpretation, I have to set the value somewhere. And so you set it so that this is the proper time of a clock far away. And then the Killing horizon is that somewhere there's a null surface, and that null surface is spanned by some null vector. Now, if it becomes null somewhere, if you have a null vector and you multiply it by 7, it's still null. So how do you normalize null vectors? You cannot normalize them. There's no natural normalization. One thing that you can do is to say, well, wait, this one, as it's a symmetry, this is also, should be careful. This one is a symmetry. Somewhere it becomes null, and so it defines a geodesic somewhere. A geodesic, we all learned geodesics to write them this way, I guess. Right? A geodesic is something with 0 acceleration. U is velocity, you derive once more acceleration 0. But if you go back and check exactly the condition that you needed, is that the tangent vector is transported in a parallel way, but you don't need to be transported into itself. Transported into itself only if you assume proper time. And so what people say is that an affinely parameterized geodesic has here 0. But it's enough to be a geodesic that it's proportional to the vector itself. And this proportionality factor, it's up to your convention, what parameter you're using around the geodesic. So now we're going to choose, we're going to make a choice. And the choice is, we normalize the vector at infinity so that word lines with this vector have a proper time given by d in dt, d in d tau if you want, psi. Once you fix it at infinity, then you cannot fix it anywhere else. And so this parameter is called the affine parameter. This one now is associated to this Killing vector that is time-like far away. And this quantity here, this one is called the surface gravity. So let me say it once more. Let's set each Schwarzschild. We have these that are Killing vectors. If you take them far away, this psi just becomes d in dt. That far away is normalized to be a time of somebody who's staying stationary far away, proper time. When you go to the horizon, it becomes null. It also becomes geodesic. This is the geodesic that spans the horizon, the null geodesic. It inherits this coefficient. And that coefficient is called surface gravity. And so one says, to say it once more, once you have Killing vectors with this condition of properties at infinity and properties that define the horizon, you also learn that there's a new quantity, surface gravity. It's dimensionful. If you check, that's dimensions of acceleration. Why? This is velocity, this is velocity. I'm deriving with respect to velocity, I'm going to get an acceleration. Okay. Now, people call it surface gravity, but are you convinced that this measures surface gravity? Like, suppose that I was sitting here at the horizon of a black hole. What's the acceleration step down?
0 years. No.
Acceleration as in like, what's the rocket thruster would.
Exactly. So there's a black hole. I want to sit just outside the black hole on a trajectory that keeps me at fixed radius, just outside.
Infinite.
It would be infinity, yeah? A bit outside would be very large. Far away would go to 0. This thing, people call it surface gravity. It's finite. We're going to compute it. But we said it should be infinite. We have to clarify this. This we have to clarify. Okay? So first I'm going to compute it slowly. No, this is the calculation to be done. Slowly means, let's take Schwarzschild. You recognize it. Let's find the killing vector that we are interested in. For this one, d in dt. Yes.
So, if you have a light ray that's traveling on the horizon, then that's a geodesic, right? That's
Yeah.
a geodesic. But then a massive object traveling there is not.
It's not a geodesic. Yeah, you're right. It's a good point. Okay, so this one is the killing vector we're speaking about. You want to check, or it's immediate. Don't do this calculation. This is the long way. You just see there's no time dependence. It's killing vector. And now this is a killing vector, but I want it to be normalized to -1 at infinity. When you compute the normalization is this factor here. And so when you look at the normalization, you find that the normalization is 0 at the horizon. Good, it's null. And at infinity, it's -1. It's also good. We're good. We don't have to fix anything. Okay? So this is check. We go to the horizon, it is 2m, it goes to 0, check. So R equal to GM, we proved that it's a killing horizon. Not surprising. We haven't computed the surface gravity. Now we do the calculation. Is it hard? Not really. You do have to know just one thing. So you want to compute this acceleration. This acceleration, you compute it by taking this derivative and then this Christoffel coefficient. This derivative is 0. Why? Killing vector, this is not gonna derivative time. This one is the one that you have to take into account. You see, this is really what Newton would call the force, gravitational force. Now, mistaking Christoffel coefficients for a force. So this one, this coefficient is the only one that you really have to compute. If you have never done it, I'm going to share a notebook done by hand in mathematics that computes all the Christoffel coefficients, all Riemann, so that you have a place where to go look at them. Find your own way of having don't do these calculations, you do them by hand the first time. But then you need a way, a place where you go, you put your metric, you have a metric, and you want to know what are the Christoffel coefficients, what are the Riemann tensor components, and it has to be efficient. It has to be like, sometimes it's always just Schwarzschild, but it's in different coordinates. So sometimes it's some surface and you want the properties of that surface. Make sure that you have a code that you trust. You put things in and you get an answer immediately. Okay? With your own conventions. I have my own, I'm going to share it, but it's going to take longer to understand what I did than to make your own. At least that's how I feel all the time. Once you understood the logic, do it by yourself. And so you do it. I'm not going to do it by hand. And say it's this one. And so what did we learn? This is proportional to this because dt is this one. And so the surface gravity is just 1/4gm. Done. This is easy to remember. This is one of the things that you have to have in your list. What's surface gravity of a Schwarzschild black hole? 1/4gm. The form, maybe it's the only thing that you have to remember. It's an acceleration, 1/m. It's the only scale that there is there. How do you find an acceleration? Okay, so now we have the number. You have the number, and the objection is immediate. The objection is, if this is surface gravity of the horizon, in the sense of its acceleration that you have to hold at the horizon, this doesn't make sense because the acceleration you have to hold at the horizon is infinite. So why we got something finite? So this we're going to address. Yes.
Oh, so you wrote that on H dt is equal to, what is H? I forgot what
H is horizon.
Oh, at the horizon.
No, the statement is, this one is not a geodesic. It's accelerated, but at the horizon becomes null, it becomes a geodesic. And at the horizon, defines this one. Okay?
And then why was dt equal to 1 minus 2 gm dr?
This is at the horizon. I should put an H on top.
Maybe I'm just missing my.
Yeah,
the
yeah,
equality
yeah, I
numbers.
understand. I understand. I understand what you're saying. And you understand what you're saying. I'm following this trajectory. So you drop this one, you set this one to 0, you have here a dt. You can also write it as dr times a coefficient. Okay, it holds, like you don't have to think of it as holding everywhere, it holds only on the horizon. Okay, so maybe it's good to put this sign on the arrow always to make sense. It's the value only on the horizon. Okay, more questions? Yes.
How can we just draw R squared over here?
This one, why? Yeah, because it's radial. Okay, I have to explain what I did. I was saying dt is a time-like-Killing vector. Now I'm interested in the value of this time-like-Killing vector on the horizon. And I'm saying you can write it in two equivalent ways, because on the horizon, these null light rays they don't change the angle, they don't wrap around, and they are null. And so now there's a relation between dt and dr. That's what I meant. So a shorter way of saying it is they are radial.
But it wouldn't be 0 inside or outside.
Exactly. Okay, so I think I should step back, explain this thing that the acceleration of the horizon is infinite, make sense of it by saying, oh, if you are just outside the horizon, how big is it? And then we go back to that. And this is one of the estimates that I want you to do, I don't know, maybe next time. Sign up for order of magnitude estimates. So I'm really saying, here we know 9.8 meters per second squared. Here we know you have Firefox, right, on your phone. I hope you do. No, here the acceleration my accelerometer is measuring 10 meters per second squared. Okay? And why? Because this thing is pushing it, so that it's a constant radius. And so if I go back, I want to do the calculation of acceleration at constant radius and make sure that I have a sense of why it's measuring that value. So let's work it out. The metric here is Schwarzschild because we are outside here. Okay? And so 2gm is at about a centimeter. There's lots of rock here, and I'm here. What's my forward velocity? One would say it's dt, but I'm not at infinity. I should make sure that I normalize this to 1. So this is the normalization coefficient. What is my acceleration? Well, acceleration is the derivative of the velocity in the direction of the velocity. Work this out if you haven't done it. If you have never done this calculation, you know online there are my lectures from GR1. Lecture 19, this one is done in 2 pages. If you've never done it, make sure that you know how to compute your acceleration. You work it out and you get this simple formula. No, that if you are farther away, your acceleration is smaller. If you are higher up, your acceleration is smaller than down. Makes sense. There's something that doesn't make sense if you look at it the first time. It is, wait, but this says that my acceleration doesn't diverge at the horizon. What am I missing? Well, this is a 4 vector. This is not the acceleration that a detector, that an accelerometer measures. Accelerometers don't measure 4 vectors. Accelerometers measure acceleration. Accelerometers have a frame, a Fermi frame. That means they carry a clock and they carry directions that don't rotate. And what you need is to find one of these directions, for instance, the radial direction, this one. You normalize it, and then the acceleration the accelerometer measures is an invariant. It's the scalar product between the acceleration and the direction of the detector. Accelerometer doesn't measure the metric. Accelerometer measures something that has to do with the metric and the accelerometer. If you move the accelerometer, you get a different answer. That's what I was doing before. So you see, it's an invariant that is built out of three things. Okay? So when you take the product, you find from here, you get this piece. And from here, you get this piece. And therefore, now you see the acceleration depends on the radius and diverges at the horizon. Here, I'm far enough because I'm at 6,000 kilometers compared to a centimeter. And so I can neglect all this, and this is all I need. And this is really g, small g. Gm over r squared is really small g. Check. If you haven't never checked, check, you get 9.8 meters per second squared. If here you put mass of the Earth, and here you put 6,000 kilometers. Okay? But it's just because you are neglecting this one. But if you are close to a black hole, this one becomes the dominating effect. Are you with me? Is this clear? How big is this acceleration? So suppose that you have a solar mass black hole and you are at 3 GM, not at 2 GM. Do you faint? So the question is, to stay at 3 GM radial, stationary, nothing is changing, you are not falling, you are outside the black hole. What is your acceleration? Is it larger or smaller than 10 G? That's what I'm asking.
3 GM.
3 GM. You can do it now. This is my question as an estimate for maybe next time. Check that you can stay at 3 GM from a solar mass black hole. Maybe not, maybe yes. Check. Okay? It's clear that at some point this piece is gonna dominate. So the question is, when is it gonna be too big for you? Okay, let's go ahead. Anybody got it, the number already? The question is if you have a quick trick for doing it. I have a quick trick, but I want you to come up with the trick. I know this one is G. I know this one is 6,000 kilometers. I know this one is 3 kilometers. I have to be careful. We want to do it for the sun, so I should not. I let you do it. I have a couple of tricks that is you replace things that you know. You multiply the divide so that you get first all the things that you know, and then you get just a dimensionless factor. That dimensionless factor is the one that you have to check. Is it 10 G? Is it 1,000 G? Convert everything in terms of quantities that you recognize. That's what I'm saying. Okay. So we have acceleration. We are convinced that the acceleration at the horizon is infinite. Let's solve the puzzle of why surface gravity is 1 over 4 GM. Why everybody calls it surface gravity? Because that's the question is it just a name? Is it by analogy, or does it have a meaning? I can say it more strongly. People really take seriously this quantity, but can you measure it? Is it made of paper that I do a calculation, this thing arises and it's nice to give it a name? Or is it something that you operationally can measure? And so last step. So if you are accelerated, it means that there's a force. So suppose this is 100 grams. Suppose that I want to hold it. What force should I apply? Should apply 100 grams times G, that is 10. It's 1 Newton, right? 0.1 times 10 is 1. You have to apply 1 Newton. And to check that I have to apply 1 Newton, one way to say is, suppose that I pull the string a little bit, how much work should I do to pull the string a little bit? Well, the work is the integral of the force times the displacement. And as we have seen that the force now depends on the distance, I really have to do this calculation, force times displacement. And so if you do it, the work that I have to do, there's a black hole down there, and I want to pull this one a little bit. What's the amount of work that I have to do? I have to do this amount of work. Check, if you drop this one, is the calculation you have done in mechanics already. This is the only correction, this one, okay? Now, there's a second thing that you have to be careful with. This delta R, is this delta R really by how much I'm pulling or not? Well, be careful because the length is not delta R. R is aerial radius. Radial distance has a coefficient that you can go check in the metric. It's this coefficient. It's all of this square root that is length, not the R. Don't forget. And so let me write it again. What's the amount of work that I have to do? It's delta L times this quantity. Or if you want, the amount of work is mass times acceleration times delta L. This A is really the acceleration we computed before. F equal ma. It holds if you use the correct F and the correct A. Okay, so now I'm going to do the extreme case. There's a black hole. I have this rope. The rope is ideal in the sense that it doesn't carry a mass, or it's negligible with respect to the weight. I'm going to pull it down till it reaches near the horizon of a black hole. I'm not standing near the black hole and pulling. I'm far away. I'm far away and ask, what's the force that I have to apply far away to the string so that this mass, I can hold it just near the black hole? Let me be clear. For the mass to be just near the black hole, it has to have an acceleration is really large. When it goes to the black hole, the acceleration is infinite. If I had to do it with rockets, I would need infinite power. But I'm doing it from far away by just holding the rope and assuming that the rope doesn't break. That's the idealization, that the rope doesn't break. What is the work? Well, the work at infinity is just this factor, and this factor is what people call the surface gravity. Surface gravity is m times surface gravity is the force that I have to apply to the string at infinity. A way of thinking about it is that you can think of this as a redshift factor, and as I'm far away, there's another redshift factor that cancels it. No, you want the string is all together electromagnetically, and every part of the string to attach to the other one does it electromagnetically, and electromagnetic interactions are redshifted, like photons are redshifted. Okay? So from this argument, I hope I convince you that if you want, you could hold a mass just at the horizon by pulling a string from far away. The problem is that the tension of the string will go to infinity, but you could still consider the limit under the assumption that the tension of the string is high enough. And I think I should put in a number now, because all these were arguments about an idealized situation. 1/4 gm, what is it as an acceleration? M is 3 kilometers. M is 3 kilometers. You see how I speak. M, in the sense of Schwarzschild radius, is 3 kilometers. You know that 1 light year is g. There's a 10 to the 13 factor. It's going to be 10 to the 13 g, or if you want, Yetis. Okay, this is the acceleration. And so if I have 100 grams, I have to put 10 to the 12 newtons to hold it. It's not infinite, but you're not going to hold it anyway. Okay? Okay, good.
I still don't conceptually understand why you take a finite force on string to hold it.
Yeah, so you see there's this factor here and this factor here that they cancel. So the question, that is the mechanism. The question you ask is, what is this mechanism that gives a cancellation of a diverging factor with a factor that goes to 0? And so on one side, there's what you're noticing. The acceleration at the horizon is infinite, or at least it diverges in this way. But then there's another effect that is, as I'm pulling from far away, there is a redshift factor that is also going to 0. And they are exactly the same.
Why do you call it the redshift?
So if I am at the horizon and I shine light out, at infinity, light is received as redshifted.
Yeah.
If I shine from the horizon to infinity, you're going to find infinite wavelength, infinite redshift. If you want, the horizon is a surface of infinite redshift. Okay? What is the redshift factor? It's exactly this factor that appears here. Why is it appearing here? Well, you can think of it as to hold the string here. You first have to hold the string here, and then this part has to hold this one. And these intermediate pieces are all electromagnetic. Holding just means that there's an electromagnetic force. And it's that same electromagnetic force that is redshifted. So what I'm saying is that the detailed calculation gives this answer, and the answer is reasonable in the sense that it fits together with all the other things that would have to fit for consistency.
So when the electromagnetic force gets redshifted, it's basically easier to hold
Yeah.
because of the
Yeah.
shift.
Yeah. And so from infinity, you could hold it. No? And that concludes this part. Yeah, so this addresses again your question. This thing that they call surface gravity is that limit at the horizon of the acceleration, which goes to infinity, times the redshift factor that goes to 0, and the product of the two is finite. And so sometimes that's the way people write it. Okay? Why all this speaking about this quantity that you saw is defined in this complicated and natural way? Why people care so much about this quantity? I think I should tell you the reason is this first laws. We don't have to derive them, we don't have to understand all the details, but these are the mechanical laws of black holes. There is nothing quantum with them, they are properties in general relativity, but they are properties of this kind. If you change the mass of a black hole, its area is going to change. If you send something spinning into a black hole, its spin is going to change. If you send some charge into a black hole, its Newtonian, its Coulombic potential is going to change. Okay, what is the law? Delta M equal these things that you could understand. No, you put in angular momentum and changes the angular velocity. You put in charge, changes the potential, but it changes also the area. The coefficient that appears here is surface gravity. That quantity we discussed before. And if you read it a bit more carefully as this is delta energy, and this is TdS, where this is entropy, then this is temperature. You recall before I said that Th bar over M, put in the numbers, there's H by G, and that is T equal H bar times surface gravity. Surface gravity gives you the temperature. Surface gravity times H bar. If you are just outside a black hole, you would see radiation of very high temperature. But if you're far away, the radiation is redshifted and you get it at this temperature. But if you stay just outside, you have to have this large acceleration, and you see lots of radiation of very high temperature. It's a physical statement. No, you use it to boil water. Okay. Radiation, it's hot, and gets redshift at infinity. Okay? So, well, these are mechanical laws for black holes, where there are quantities that are defined at infinity. The mass, we learned you define it at infinity. We haven't learned it yet, but also the angular momentum and the charge, you define it at infinity. And then there are other quantities, the temperature, velocity, the potential. These are defined at the horizon. And these are statements about take one black hole, you perturb it a little bit, and you ask, what does it go back to at equilibrium? Okay? I think I should stop there. I have lots of examples, and I don't think it's the right time to do examples. I only wanted to show you, maybe I have to show you one more. Yeah. Only this one. So if you don't change the angular momentum, you don't change the charge, then it's delta m equal delta area of the horizon times surface gravity. Multiply and divide by h bar. And then this is temperature and this is entropy. And so it's a formula where there's no h bar, but it's because it's canceling between two pieces. Okay. That's all I wanted to cover. There's time for a couple of questions. Temperature and entropy. These are temperature as dimensions of temperature. It's really entropy with dimensions of entropy. So you can really think of thermodynamics of liquids. Yes.
The first law tells us that if I change the mass, how the area and the angular momentum changes. But does it tell us by how much or what's the relative proportions when they change? Like how?
Yeah, no, it doesn't. That's yes.
In the first law, I can conceptually understand what a delta A or a delta angular, I don't understand what a conceptually a change in charge of a black hole, just like sending.
You drop a charge. Yeah.
Right.
Yeah.
So we can only. Yeah. Right, but wasn't there something about the charge wasn't neutralized?
Yeah, I see. So this is the story of time scales. You put in a charge, and then the black hole becomes charged. Then you can ask, is it going to neutralize? Well, now it's a charged black hole. If there are other charges around, it's going to attract them, neutralize. You work under the assumption that it's isolated enough. Because these are statements about equilibrium. This is near equilibrium thermodynamics.
Yeah, but I think part of my confusion is you, right? It's like, okay, you look at a delta M, right? Like, see, you fix delta M, delta A, and delta J, and plot between delta U, right? There's no like physical mechanism. That doesn't make sense.
So you cannot fix all of this and change this one. Like when you put the delta Q, at least you're going to change the mass. You could try to fix the mass by adding mass in such a way that it doesn't, then the area is going to change.
Is this the ADM mass?
Yes. And that's, I'm going to take it as, well, but that's weird. Like ADM mass is a space like infinity. This cannot change in time. That's the seminar of Tuesday. The seminar of Tuesday is, this is equilibrium. How do we do it out of equilibrium where things are actually changing? And we are not just comparing equilibrium things. It's a difficult thing to address and something where there's recent progress. And so there were two questions. One is this one. The other was like, does this predict what is happening? So this is only equilibrium and it's not going to predict what is happening. You need two more things for doing the two. One is the seminar tomorrow, and the other is the seminar of Tuesday. So the questions were good. It's things that people are actually working on. If you come tomorrow, you're going to hear something about two black holes. They merge, they get a final spin. Can you predict the final spin by requiring that the entropy is maximum? as these are two gases at different temperature, you put them together, what's the final temperature? You don't use the first law to predict the final temperature, you use the second. Okay, that's all for today. Thank you.